So, okay, uh, good morning again. So, this is a problem of Faraday's laws, which immediately follow Faraday's laws. The problem is that a magnetic field of 10 Tesla. So, value of magnetic field is given as 10 Tesla. X at right angle to a coil. So, there is a coil area. The coil has the area 5 square meter, that is 5 meters square. Okay, and 100 turns. Turns is 100 turns. The coil has 100 turns. If the coil is removed from the field in 1 by 10 second, that is dt, very small amount of time, it is 1 by 10 second. Find the EMF induced in the coil. So we have to find out by using these data. We have to find out the EMF induced in the coil. So this is the question. A magnetic field of 10 Tesla acts at right angle to a coil of area 5 square meter and 100 turns. The coil is removed from the field in 1 by 10 seconds. Find the EMF induced in the coil. So first of all, we have to find out magnetic flux. The magnetic flux, as we know, phi is equal BAM, right? So since it is right angle, we know that magnetic flux is nothing but it is the dot product of B vector and A vector, right? Okay, B is the magnetic field, A is the area. So if we find the magnitude only, B A cos theta, and if there are n turns in the coil, so suppose this is a coil and the area normal to the area of the coil indicates in this direction, the magnetic field is in this direction, so angle is theta, right? According to the question, the magnetic field has value, this is the magnetic field, it has value 10 Tesla, okay, no problem. But X at right angle to the coil, so magnetic field acts at right angle to the coil, right? So if the field acts at right angle like this, so what will happen? The theta will be 0. As soon as this magnetic field direction makes right angle, okay, immediately theta will be 0. When theta is equal 0, cos 0 degree is equal 1. Okay, so cos 0 degree will be 1. So NBA 1. So n is given as 100. So 100. B is what? B is 10 Tesla. A is what? A is 5 meters square. So 5. So this is the 5,000 Weber, WB, Weber. The unit of magnetic flux is Weber, 5,000 Weber. So this is the first part. Second part, you are asked to find out induced EMF induced in a coil. So you have to find out induced EMF. What you have to find out? You have to find out induced EMF. So what is your formula? That relation comes from Faraday's second law. So what is Faraday's second law? So Faraday's second law, as we have got, according to Lenz's law, the induced EMF induced is given by, according to Faraday's law, epsilon is equal to minus d phi by dt. Suppose sometimes it is written as del phi, del t. Suppose it is d phi by dt. Okay. So the negative sign comes from Lenz's law. Okay. According to conservation of energy, Lenz told that there should be a negative sign in the Faraday's second law, right? The negative sign means that the source, that the induced direction of induced EMF should be such that it should always oppose the region why it is creating. Jitu karone induced EMF hoise he karon to khodai oppose koribo. ঠিক আছে? So this is the relation Faraday's second rule. This gives the induced EMF is equal to the rate of change of magnetic flux. Okay, rate of change of magnetic flux. When the coil is removed, the coil is removed from North Pole from the magnetic field. Magnetic field খনৰ পৰা যেতিয়া coilটো আঁতৰাই লৈ যোৱা হ'ল কিমান সময়ত 1/10 second. The coil is removed. So finally, when it is removed, the change of magnetic flux d phi, it indicates change of magnetic flux. Final magnetic flux will be 0. Initial magnetic flux was this. It is the magnetic flux initially we got from the coil. Okay. When the coil is within the magnetic field, this amount of magnetic flux is produced. As soon as it is removed, it becomes 0. So final magnetic flux minus initial magnetic flux, it is 5,000. Okay. So dt is the 1/10 second. So we have to put the values here, then you will get the induced EMF. So minus 0 minus 5,000, 0 minus 5,000, 1/10. Okay, putting all the values. So minus will be plus 5,000 into 10. Okay, so 5 into 10 to the power 4 volt. So induced required induced EMF will be 5. So the next topic we'll be discussing about generation of induced EMF. The magnetic flux is given as phi b a cos of theta. The magnitude of magnetic flux is given by b a cos of theta. Okay. So you see, and EMF induced is given as minus d phi by dt. Okay, right? So change of flux with respect to time produces induced EMF. So if you put the value of phi here, b a cos of theta, okay, that is changing parameter is this b a cos theta, right? So by changing all these quantities b a and theta, you can produce EMF. মানে কথাটো হল b a আৰু থিটা তিনিটা বস্তু আছে তিনিটা বস্তু কোনোবা এটা চেঞ্জ কৰি you can get induced EMF তুমি induced EMF পাব পাৰা so three ways to produce induced EMF tinita way hole number one by changing B that is magnetic field okay magnetic field strength so if you change B with respect to time you will get induced EMF one of the way number two by changing A area of the coil that is area of the coil second the third one is theta is the angle between B and A okay the third way is by changing theta the angle between A vector and B vector so you know area in general area is not a vector quantity if you represent area with a direction so then area will be a vector quantity if the normal drawn on the area represent the direction of the area then it will become a vector quantity normally area volumes are not a vector quantity so area may become vector quantity as soon as we represent its direction right when magnetic lines of force pass through it it makes an angle theta okay so this angle by changing the angle this is the direction of magnetic lines of force when we change the orientation direction okay either by rotating magnetic field or by rotating coil anyone if we rotate the coil okay then theta will change that is by changing the orientation of A and B that is theta we can have induced EMF this is important out of all these three ways the last one is most practical that is by changing theta the orientation between A vector that is area vector and B vector that is magnetic field we can change the first method to produce induced EMF by changing B is not practically applicable if you change B at any moment it is a tedious job to produce induced EMF but you will have to study how to get induced EMF by changing area okay this is a little bit study and but theta by changing theta to produce induced EMF is most important so we'll study so let us see how we can have induced EMF by changing area generation of induced EMF by changing the area of a coil okay so we'll change the area of a coil what we'll do we will just change the area of a coil so let us see suppose this is the uh, shape of a conductor, current carrying conductor. Okay, so A B, A C B, and it is this AB is the conductor which can be moved forward and backward. Okay, suppose to A dash B dash, right? Now initially, suppose it was the area CAB. CAB is the initial area. Initial area. Initial area is CAB. So final area. Final area. Final area is A dash, A dash, C, B dash. This whole area. So change in area. Change in area. Okay. Change in area is equal. Change in area is equal A dash C B dash minus C A B, which is equal to this one A dash A B B dash. This area, okay, this area A dash A B B dash. So let we can move this conductor, okay, forward and backward, forward and backward. So initially, this is the area that is, it should be loop, okay, coil should be a loop. So this is the affected area for which induced EMF is obtained. So as we told that, as we are discussing that, the flux is V A cos of theta, okay. So we are changing area, but B and cos theta are remaining constant. So epsilon is equal to minus d phi by dt. So since B is constant, cos theta is constant, right? So minus B cos theta will come out, and dA by dt will be there, because A is the only changeable quantity, right? So A is the only changeable quantity. So we want to find out change in area. Okay. Let us see how we can find induced EMF. Okay. Let V be the velocity. Okay. Let the conductor AB is moved with velocity v in time dt to position A dash B dash. Okay, this is change in area. Already we have calculated change in area. So A dash B dash, is a new position. We have taken V to this. So this distance is V dt. What is the time taken? Dt is the time. So velocity into time gives the distance. So B dash is the distance. If this is the length of the coil is L, the area will be L V dt. Okay. So area is L V dt. So V is the velocity. If you multiply V dt, it will give the distance. So distance into length, it is this rate into length, give the area, change in area, L V dt. Okay. So that is d phi. D phi is equal now let me show you. Now d phi, that is change in magnetic flux. The b, okay, b already you have calculated that b d phi is equal this one without writing dt. Okay, b cos theta dA. dA is a change in area. So if theta is 90 degree, theta is 0 degree, here theta is 0 degree, it will be 1. So b dA. So what is the value of dA? So this is just change in area. So this is dA. Okay. So b L v dt, right? We are taking only the magnitude, therefore negative sign is not required here, right? So b L v dt. Now d phi by dt, dividing both sides by dt, b L v. So alternately gives the induced EMF. Okay, this gives the induced EMF BLV. What is B? B is the magnitude of the magnetic field. L is the length of the coil. B is the length of the conductor, and V is the velocity of the conductor. Right. So if you consider the modulus, that is magnitude, then no negative sign is required. If you write only the direct value, then negative sign is required, minus L V. Okay, from Faraday's rule. Okay, so if you write modulus, then no need to write the negative sign. So this is the one of the important relation you will be need to solve some problem when you change the area by changing the position of a coil. Okay.